Now. So welcome everyone to our edition number 181 of these Latin American webinars on high energy physics. So today we are super happy to have Amitayus Banik from South Korea. So actually he got his PhD a couple of years ago in Würzburg, Germany. And after that he moved to South Korea. And today he will talk about phase transitions, gravitational waves, and so please, Amitayu, the stage is all yours.
All right. So, okay. So my screen is still visible, right?
Yes.
All right, great. So hopefully no technical difficulties. So thank you, Nicholas, for that kind introduction, and thank you and all the organizers for this invitation and this opportunity to present this fairly recent work that I completed with some collaborators in the US, namely Yanuswi Udaisai and Yushin Sai. I think the best way to begin this talk would be to let's dissect the title one by one. So firstly, let's talk a bit about um, pulsar timing arrays. So there are experimental collaborations related to these, such as Nanograv, the European Pulsar Timing Array, the Parkes Pulsar Timing Array, and the Indian Pulsar Timing Array, just to name a few, which have been taking data over the last decade or so. And what is the data that they take? So in our galaxy, there are pulsars, which are essentially rotating neutron stars, and they emit periodic pulses that you can detect on Earth. So there are a bunch of them. And what you can do is take two of them and calculate the correlation between these pulses as they reach on Earth. And you can calculate this. And what you would expect is that, well, the time arrival of one pulsar should not depend on the other. So they should be uncorrelated, so to speak. But that's not what these collaborations see. What they see is these blue data points. And you can see within the error bars, they seem to be consistent with this black dashed curve. This is known as the Heilings-Downs correlation curve. And what that indicates is it's a theoretical prediction that you have a stochastic gravitational wave background passing by. And this is in the nanohertz regime. So because the observations seem to be consistent with this, this is essentially a smoking gun signature that there's a stochastic gravitational wave background somewhere in the nanohertz regime. So this is the first ever stochastic gravitational wave background that's been observed, and hence that's why it's so significant. So naturally, you would want to know what's the origin of this. For gravitational waves, there are typically two well-known sources. The first is if it's astrophysical in origin, and that's the leading or canonical explanation, so to speak, of the PTA signal. So it's believed to be coming from a merging population of supermassive black holes. So as we know from observations, like in the in-spiral stage of black hole binary mergers, these emit gravitational waves. So the idea is that you have a bunch of these, a large population that emit gravitational waves, and this explains the PTA signal. There are a few issues, or I'd say subtleties with this, however. The first point is that the exact population size of supermassive black holes that produce such a large signal is currently still being investigated. So from observations, we know there are more supermassive black holes than we previously thought, but the exact population size is still under some debate. The other slight issue is this final parsec problem. So to briefly explain a bit about this. So the binary merges because you have power losses in the orbit. This can go to gravitational waves, or if there's some kind of environment around the black holes, so matter and so on, this can also induce power losses through what's known as dynamical friction. So it's just acts as a friction force that's reducing the energy in the orbit and causes these guys to merge. So the timeline is as follows. You have matter on the black holes, and as the matter induces power losses, eventually you shrink the orbit such that the separation distance between them is about a few Schwarzschild radius, and then they start emitting gravitational waves, and you get the PTA signal. The catch is as follows. Simulations have shown that for supermassive black holes, um, the matter around the black holes while they're in spiraling is cleared out at the level of, say, a few tens, hundreds of parsec. And why this is being cleared out is that there's a kind of feedback effect. So as the orbit shrinks, it releases energy that can directly be given to the matter environment, and it essentially gets ejected out. So at around 10 parsec, there's no matter around these black holes to cause dynamical friction. So you would think that, okay, then what's the problem? You could emit gravitational waves, and yeah, that's fine. That can induce power losses. The issue is that for the supermassive black holes, the Schwarzschild radius is about one parsec or so. And gravitational wave emission is really efficient at the order of a few Schwarzschild radius. So now you can see the problem. At about 10 parsec, there's no matter for dynamical friction. But you need to shrink down to 1 parsec, hence the name final parsec problem. So there's not really a thorough, well-known mechanism on how you get from 10 parsec down to 1 parsec. So this still needs some better understanding. So this was about astrophysical sources. You can now turn to cosmological sources of gravitational waves. In the context of the PTA signal, collapsing domain walls, radiating cosmic string networks, so these all emit gravitational waves, have been well studied. You can also have phase transitions as the source of gravitational waves, and that is what we'll consider in this talk. So we'll be focusing on first order phase transitions occurring in some dark sector. So the environment around when this phase transition occurs is quite dynamic. So you have bubbles of the true phase nucleating. So they start forming, they expand, they collide, and as they propagate, this all can source gravitational waves, as we'll see later. So this is actually the sounds that I refer to in my title. And what we try to do is that we focused on thinking that, okay, so you have the PTA observation. Can you directly somehow connect this to the underlying particle physics model? So for a phase transition, you can describe it and characterize it in terms of the so-called macroscopic phase transition parameters. That refers to the strength of the phase transition, the temperature of the phase transition, and also the duration. This is, of course, very useful information. However, we pose the question that, say you start out with some dark sector Lagrangian that has some couplings, some particle content, and then you have the PTA spectrum. If a dark sector phase transition is indeed so gravitational waves produced from this dark sector phase transition is the origin of this PTA signal, what can you learn about the parameters in the model? So that is the underlying theme of this talk and this work that was done. And so it's best now to understand how to do this. So we need to know how to essentially boil the universe. So that requires a recipe book in the following form. We need a model first. So we need our ingredients. To cook up a phase transition, you need at least a scalar degree of freedom. Why? Because a phase transition is typically associated with some spontaneous symmetry breaking. So a scalar usually needs to acquire some vacuum expectation value. That's the easiest way to do it. Additionally, you need some extra bosonic degrees of freedom to enhance the phase transition. More about this later. So based on this, the most minimal model you could think of, or rather we thought of, was that if you start off with some dot U1, which is gauged, and the particle content starts off with at least a complex scalar phi. Since it's gauged, there's a dark photon. So this is the A prime. And this couples to the complex scalar with gauged and GD through the covariant derivative. And then usual spontaneous symmetry breaking, you have the usual relations between the vacuum expectation value and the parameters in the scalar potential. This vacuum expectation value is acquired in the real direction of the field, where phi, small phi now is the dark Higgs. So that's a physical field. Alongside this, you can also consider the limit of enlarging the symmetry group. So instead of just U1, you can promote this to a larger rank, so SUN. You have to do this a little carefully, however, because you need to enforce that this SUN is completely broken. Otherwise, you may end up with some remnant massless degrees of freedom, and those are strongly constrained by cosmic microwave background observables. So what we'll assume is that if we take SUN, this all the n square minus 1 gauge bosons that are there acquire masses, and this should be roughly of the order of the VEV, this V0 here. Finally, I talked a lot about, I kind of stressed that you need bosonic degrees of freedom. You can also think what happens if you add a Yukawa term. To put this in the potential, what you need is a Dirac fermion and some singlet. So therefore, you get this Yukawa coupling with the complex scalar phi. This does not directly affect the phase transition dynamics, as we'll see later, but it can indirectly impact some of the phase transition parameters. So we'll see this in details. Okay, so this is the key ingredients. So essentially now we have the liquid that we want to boil. Now we have to understand how it boils. To do this, we have to consider the effective potential at finite temperatures. So the standard procedure is that you promote the zero temperature V0 to some background field phi, which is a function of temperature. And the temperature evolution of this phi field is governed by the finite temperature effective potential, and it's given as follows. So for those of you who are a little unfamiliar with this, the idea is just to draw some correlation. The idea is that, okay, the zero temperature field theory part is that you have the one loop effective potential given by the tree level part and then the Coleman-Weinberg part, which comes from this trace of the logarithm of the propagator. Essentially, this QFT at finite temperature is essentially the same thing, except that when you do the trace is essentially an integral over three spatial and one temporal dimension. What you do in finite temperature field theory is that you do the integral still over the spatial dimensions, but you perform a sum instead over the temporal direction. And this sum is over what's known as the Matsubara modes. Once you perform a bit of algebra, you can see that you can extract these various pieces as such. And explicitly, these are, you have the tree level part, which is the familiar Mexican hat potential. Then you have the one loop corrections, which is so one loop corrections at zero temperature. So this is the well-known Kuhn-Weinberg potential. And what's important this is that finite temperature field theory does not introduce extra ultraviolet divergences. So all the ultraviolet divergences are encaptured in the zero temperature part here in this way. And that's precisely in the Colin-Weinberg potential. So you need to do some renormalization. So we'll work in the on-shell scheme in Landau gauge. And this is the expression. And note that, which will be important later, for fermions come with a relative negative sign with respect to bosons in the effective potential. You have the field-dependent masses that are determined as usual. Now, explicitly, the finite temperature corrections look as follows. And yeah, this is, yeah, again, finite in the ultraviolet. And this is usually known in the literature as the J integral. So this finite temperature effective potential gives you the thermal evolution of the wave. So now you know how the liquid boils, and the picture is as follows. At high temperatures, as confirmed by the effective potential, the phi field lies at the 0 point, so the symmetry is intact. What you expect is, and what's also confirmed by the effective potential, that at low temperatures, the phi field ends up in the true vacuum here, and their symmetry is, of course, broken. What's important for us is that in between these two temperatures, there is some barrier being formed between two degenerate minima. This barrier forms at some critical temperature Tc in between T1 and T2. And this separates the two degenerate vacua. And this can be used as a classification to say that the phase transition is first order. In other words, the phi field functions as the order parameter. And if you track its thermal evolution, you'll see there's a discontinuity close to the critical temperature. Okay, so this is the basic picture of what we want to see. As it'll become important later, it might be wise to understand like what's the strength of the phase transition. So you have a first order phase transition. How do you say it's a strong first order phase transition, for example? From the particle physics point of view, you can think of the parameter Vc over Tc. So Vc is the critical value, the value of the VEV at the critical temperature Tc. And just for some intuitive understanding, you can consider the pure U1 model. So no fermions, just pure U1 gauged. So there are three free parameters. And if you fix the parameters in the scalar potential mu and lambda, and just vary the gauge coupling, the following picture emerges. So you can see that increasing the gauge coupling seems to make the separation between the degenerate minima wider, and it makes this barrier larger. What's also confirming the strength of the transition is that, okay, so for the blue curve where you had this, you can barely see there's a bump there. There's a very small barrier being formed. The transition is quite weak with Vc over Tc about 0.25. Then you have, for the green curve, as you dial up the gauge coupling, it's about 1.6. So yes, there's a definite barrier there. And of course, as expected for the red curve, it's much larger. So I want you to keep in this mind that certain parameters lead to this barrier being larger. And this will become quite relevant for our further discussion. Okay, so this is the behavior of the liquid. So this is the different kinds of liquid and how they can essentially boil. Now, if anyone's done any cooking, or at least if you've boiled water, you know that you can't, you have water, but you need a boiler at the end of the day. So to boil water, you pick up a pot. In our case, the pot is the universe. And for the universe to track the only thing that can evolve essentially as the function of temperature is the Hubble. That gives the expansion rate as a function of temperature. So essentially, our universe acts as the pot, and this, and this is basically the liquid that we're boiling. And again, drawing the analogy to water, you know that when you're boiling water, bubbles of the new phase start forming. So bubbles of steam start forming as you boil water. So it's a similar picture here. First order phase transitions proceed through bubble nucleation. And the rate at which these bubbles of the true vacuum form, normalized to the Hubble volume, is given as such. Here, S3 is known as so this is the O3 symmetric Euclidean action for the bounce configuration of the scalar field. And this is rather non-trivial to obtain. You have to solve a differential equation. So we obtain this numerically using the Mathematica package find bounds. The idea of this gamma of t is that you're describing the transition rate from the false vacuum to the true vacuum by jumping over that barrier that I had shown you. So how effectively you can jump over that barrier due to thermal fluctuations. So this is also known as the thermal transition rate. And now, as I mentioned, you will now have your pot. So the idea is that when this nucleation rate is comparable to the Hubble, bubbles of the true phase start forming and expanding, and eventually your universe ends up in the true phase and overtakes the old phase. And assuming radiation domination, your Hubble squared scales as t to the power 4. And let's see this in action. So again, this is the U1 model that I had just shown you. And similar mu and lambda are fixed. And I've just varied the GD as the colors. So you can see for GD equal to 0.75, oh, and the black line is the Hubble. The intersection points tell you that that is the nucleation temperature because this equality is satisfied. So you can see for the green line, it's almost vertical. The reason for this is that the barrier formed, if you recall, is rather small. The barrier is there, but it's quite small. And therefore, you don't have to really wait a lot. So the universe takes care of it. So as the universe is expanding and cooling, you don't need to wait so much, and you can easily achieve nucleation. So this is quite close to the corresponding critical temperature. So, okay, one more word okay, this boiling analogy kind of breaks down, but I think because instead you're cooling instead of, well, heating, but it's still a nice picture to keep in mind. So again, here, small barrier, it's quite easy to achieve nucleation. Now, for the red curve, you have a much larger barrier. In this case, you need to wait a bit. So what you're waiting for is the barrier to fall down a little. Eventually, when it's fallen down enough, then this equality is achieved and the scalar field can transition from the false to the true vacuum. Now, if the barrier is way too large, so increasing GD, you can always do that. The barrier is still large. You can reach a point that it never actually meets the Hubble, and therefore nucleation is no longer achieved for such a parameter point. So this is the basic idea, and it shows the interplay between the particle physics and the cosmology to fully encapture the phase transition dynamics. And one more thing I would like to mention, of course, we're assuming here standard cosmology, so radiation dominated. You can also consider perhaps other cosmologies. So Nicholas and I, along with our collaborator Fazlullah, we looked at the effect of phase transitions in other cosmologies, and I'd implore you all to have a look at our work. It's quite recent. But for the rest of this talk, I'll be assuming standard cosmology, so radiation dominated. All right, so to complete the picture for the phase transition parameters, we have the nucleation temperature. Additionally, the phase transition is characterized by its duration, or rather its inverse duration, which is beta, and another parameter called alpha, which is related to the latent heat you release from the phase transition. And these are given as follows. So beta is related to the derivative of the action, and it's usually counted in terms of the number of Hubbles, so beta over h star. Similarly, alpha star is a sort of better description because it actually tells you that, okay, there's a link between the cosmology as well. So alpha star is the potential difference. So that's the latent heat that you've released, normalized to the radiation density at the nucleation temperature. Now, you can note in all of these, you have the one loop effective potential here. The S3 over T depends on the one loop effective potential. Gamma, it depends on S3 over T, and that depends on the effective potential. Now, the effective potential contains all the particle physics. So you can see that it essentially acts as a translator between the phase transition parameters and the model parameters. So let's see this in action. Let's consider the pure U1 gauge group for no fermions for now. Let's fix the value of lambda. And to get a feel of this, we can study the phase transition in the mu and coupling plane. So the only other available coupling is GD. Here is, for example, the nucleation temperature. And this is in the plane of GD versus mu. And these two regions, I'm sure we're all now very accustomed to right now. No nucleation means the scalar field is trapped in the false vacuum. The barrier is too large. You cannot transition. Not first order just means that the barrier formed is too small or negligible. And this is, so barrier barely formed. So this is the regime of either phase transition is second order or crossover. You can also have a look at the inverse duration, so beta over h star. This looks at, and also the phase transition strength. What you can see here for these two plots, for a fixed GD, if you vary the mu, the inverse duration and the strength of the transition are relatively insensitive to the value of mu. However, the mu changes the scale of the T star. So what mu is doing is, for example, if mu is of the order of 10 MeV, your phase transition temperature is also going to be of the order of, say, 10 MeV or so. So mu fixes the relative scale of the phase transition temperature or the nucleation temperature. I'll use them interchangeably. Okay, so now we understood the role of mu. Let's look at the role of the couplings. So for now, we fix mu about to say 2 MeV. That means your T star will be somewhere in the MeV range. We're still keeping the fermions out of the picture. And let's first look at the T star in the coupling plane. So here you can see that the exact value of T star is fixed by the couplings. So the scale is set by mu. The exact value is set by T star. And T star, again, becomes smaller and smaller as you approach the edge of no nucleation. This is because, again, it's all related to that barrier. If the potential barrier is large, you need to wait longer. So your T star shifts more and more away from the critical temperature. So that's why it becomes smaller and smaller. So that's why across this no nucleation boundary, the T star is smaller and becomes close to, it becomes quite close to mu. In the opposite extreme, if T star, as it becomes not first order, so the barrier is quite small, there the T star becomes a bit larger and becomes closer to the critical temperature. So that's the exact value of the T star. With this, we can now look at the duration and strength of the phase transition, or rather the inverse duration. So here again, as you approach the boundary of no nucleation, This boundary of no nucleation is essentially achieved if you fix your lambda and increase the GD, or if you fix your GD and lower your lambda. Both of these result in a larger barrier. So larger barrier just means that you need to wait longer for it to cool, and therefore your phase transition is longer. So your beta over h is actually smaller. Recall beta over h is always the inverse duration. And as expected towards the boundary of not first order, beta over h is quite large. A similar trend again for the latent heat. So both of these kind of monotonically increase as you go from not first order boundary to the no nucleation boundary. At the same, now following up on this, you can now think, let's introduce more gauge bosons. So let's enhance the symmetry. So for example, we take n equal to 2, which is the solid lines, and n equal to 3, which is the dashed lines. What we observed is that the same trends that you see for the U1 carry over to the SU2 and SU3 case. But what happens is now the purple lines that you see, the purple line corresponds to the no nucleation edge for that particular gauge group. And the green line corresponds to the not first order boundary for that gauge group. So essentially what's happening is the parameter space tilts. The reason for this is that you have more gauge bosons in the effective potential. So you need to adjust your gauge coupling correspondingly and this is what's forcing this parameter space to tilt. Now, building upon this, let's keep this parameter point lambda equal to about 0.05 and GD equal to 1.2 in mind. And let's look at fermions. So we'll just study the strength of the phase transition. And first, let's look at the non-zero Yukawa coupling with respect to the gauge coupling. And here you can see what's happening is that you're kind of unlocking some parameter space. Recall this region for zero Yukawa coupling was forbidden. The reason is that you ran into a problem that the barrier is just too large. You end up in no nucleation. What's happening here is that the fermions come with a negative sign in the effective potential. What that does is it drags the potential down. To compensate for this, you can increase the gauge coupling now. That's why this parameter space is quote unquote unlocked. And once you've unlocked this, if you dial up the gauge coupling enough, you eventually reach a comparable parameter phase transition parameter value for a larger value of GD. Similarly, you can also study the same thing for the YD and lambda in the YD and lambda plane. Again, recall that for GD equal to 1.2, lambda equal to 0.03 was forbidden. But if you now have a non-zero Yukawa coupling, you can unlock this parameter space and end up with a comparable value of the phase transition parameter. Again, it's due to the fact that the fermions come with a negative sign in the effective potential. So it's dragging it down. You increase the bosonic coupling and so on. Or in this case, decrease the lambda. So at the end, you have to tune the bosonic couplings. And this compensates for the negative fermionic contribution and allows you to get the similar potential form and obtain a comparable value of the phase transition parameter. And finally, if you dial up the Yukawa coupling too much, eventually you end up in a regime where the potential becomes unbounded, or rather the vacuum is unstable. So now, to summarize at this stage, we now have a very good idea of how the model parameters affect the phase transition parameters. So there are three of these: the phase transition strength, the duration, and the phase transition temperature or the nucleation temperature. These three are the inputs for the gravitational wave spectrum generated from a first order phase transition. And Now let's understand how gravitational waves come about from a first order phase transition. So it's, as I mentioned in the beginning, it's quite a dynamic environment. Gravitational waves are sourced from first order phase transitions through bubbles colliding with each other. These bubbles can expand and propagate throughout the medium. This induces acoustic gravitational waves, also known as sound waves. And this process also results in inducing vorticity in the medium. And this leads to the turbulence contribution. What's common to all these three is that the gravitational wave spectrum looks something as follows. So you have the overall amplitude, and then there is the spectral shape of the gravitational wave contribution with an associated peak frequency depending on the contribution. And depending on the exact underlying physics, the microphysics, a certain contribution can dominate. Because in our case, we find strong interactions of the scalar with the plasma, the sound wave contribution appears to be the dominant source for our case, and we get a subleading contribution coming from the turbulence part. Okay, so let's see this in full form. Let's consider the sound wave since this was the dominant contribution. So this is the spectral shape for the sound waves. And the amplitude looks something like this. The amplitude that I'm talking about is the amplitude that we observe today. So at the time, you have the amplitude emitted at the time of emission of at the temperature of the phase transition. This redshifts because the expansion of the universe. This is radiation dominated. So that's why you have these extra factors appearing in, especially the G star and so on. So this is the gravitational wave amplitude observed today. Similarly, for the peak frequency, this is the peak frequency of sound waves observed today. Again, you have to redshift this accordingly based on the cosmology. There's an additional parameter that appears in both of these. This is the wall velocity. This is typically obtained independently. However, in some regimes, you can, for example, if it's a strong phase transition, you can assume some kind of relation. So we assume the detonation regime. In this case, the wall velocity is proportional to the strength of the transition. In the amplitude, there is a kappa sound wave. So this kappa is the efficiency factor. It basically tells you how much energy released from the phase transition you're transferring to the bulk motion of the plasma and generating the sound waves. And note that we're calculating VW and kappa using alpha ds star. So that's essentially the latent heat release normalized to the Dot sector radiation density, because this depends primarily on the Dot sector dynamics. And for the sound wave amplitude, there's an additional factor called upsilon. This is known as a suppression factor and accounts for the fact that, well, your phase transition is not very long. It's not, well, infinitely long. There's some finite duration. And what this upsilon is tells you that, okay, if beta over h is large, upsilon is going to be small. What that means is if beta over h is quite large, your phase transition is very short, and hence it's overall suppressed because you multiply the upsilon. Now, you can see that in all of these things, the three phase transition parameters appear in some form or the other. So beta over h, alpha, and T star. And let's see what the spectra looks like. So these are the phase transition parameters corresponding to various spectra. And now you can see that for the sound wave peak frequency, the color curves have the same beta over h and alpha star. The only thing different is the T star for these. So you can see what the T star so if the scale of the T star is different, the peak frequency shifts to the left or right accordingly. For the sound wave amplitude, two parameters appear, the beta over h and the alpha star. It's not so easy to see from these numbers here, but the alpha star, what it does is it affects the overall amplitude of the gravitational waves. And finally, beta over h appears in both the amplitude and the peak frequency. Therefore, the effect is for larger beta over h, it moves diagonally to the right. And for smaller beta over h, it moves upwards. So the amplitude increases if you have a smaller beta over h. And now, so these are the phase transition parameters corresponding to this, but we already know how the phase transition parameters depend on the model parameters. So here are the model parameters that gave rise to those phase transition parameters. If you now look at the colored curves, the only thing different is the mu. So recall this curve, these contours here. So you're changing the scale of mu. Therefore, you're affecting the scale of the peak frequency of the gravitational waves. And for the GD, for fixed lambda, increasing GD tends to decrease the beta over h and increase the alpha. So what's happening here is that the GD plays the role of both beta over h and alpha star for a fixed lambda. So this is a rough idea of how the model parameters affect the gravitational wave spectrum. So now you can see we've constructed the full pipeline. You start from the model and then go all the way to the gravitational waves through the phase transition parameters. And this is essentially what we wanted to do. So now we're in a position to really tackle the pulsar timing array dataset. To do this, we first need the data itself. So by that, we need the mean values and the error bars. These are the available violin plots, which we took from this work that came out last year. So we consider the nanograph PPTA and EPTA datasets. And what we did is we tested the compatibility of gravitational waves being sourced from dot sector phase transitions with the PTA dataset through a chi-square fit. So that's a goodness to fit metric. And of course, again, the data, so these are the mean values of the PTA dataset, and these are the 1 sigma error bars. You also need, in addition, the degrees of freedom just to tell you how good your fit is. So in this case, the degrees of freedom are given by 41 minus the number of parameters. The number of parameters depend on the model you're considering. The 41 comes from the fact that there are, in this combined three data sets, there are 41 frequency bins. And typically, you have, for a fit to 1 sigma level, chi-square should be about 45. For 2 sigma, chi-square should be about 60. And 3 sigma, this should be about 70. And now, to answer the question that I posed that at the beginning of the talk, and what you've all been wondering, does this work? So here are what we found were the best fit spectra. Colored lines correspond to the gauge group, and dashed just means that the Yukawa coupling is non-zero. The lightly shaded points are the data sets that we considered from the PTA collaborations. And by eye, you can see it seems to fit quite well. And here are the model parameters and corresponding phase transition parameters that gave these spectra. And here is the chi-square value. And you can see all of these are less than 45. So this means that this is a fit at 1 sigma level to the PTA dataset. And you can see that the best fit PT parameters feature T star about 2.5, with your beta over H being 40. So it's a relatively long phase transition and quite strong because your alpha star is about 0.9. And corresponding model parameters feature large couplings. So your lambda needs to be about 0.05, and your gauge coupling needs to be order 1. Your symmetry breaking scale needs to be, so that by that I mean the mu, needs to be somewhat at around a few MeV level, similar to T star. And now you might be asking, okay, this is the best fit spectrum. How much can you play around with this? So again, let's take our very simple U1 model that we considered. You have these contours. What happens now is if you enforce a fit to the PTA data, you can see that most or almost all the parameter space is completely excluded by this, and it really zooms in on the part that is close to the no nucleation boundary. That is because you have the strongest, longest phase transitions and close to MEV scale phase transitions in that part of parameter space. So essentially what it does, and you quickly go out of the fit if you start playing around too much with the parameters. So what the PTA dataset does is that it's now really fix the couplings. You can think, okay, can I play a little bit the mu parameter? It might be smart to play with the mu because again, if you there's this exponential dependence. So you might think that, okay, I can change the T star a bit, but no, that's not really that's safe to do because you might also screw the beta over H or the alpha star. What you can do is maybe play a bit with the mu because the mu is rather insensitive to the so the beta over H rather and so on are rather insensitive to the mu parameter. What you can see here is that like, okay, there's really not, you're already close to the minima. So at these mu is fixed to 2. So you're already very close to the minima. So there's not really a lot of room to play around with. So what you've done is essentially fix the mu parameter, and this has fixed the couplings. So at the end of the day, what it shows is the PTA data precisely defines your dark sector model. And since you've really defined your dark sector model, you can consider perhaps the dark sector cosmology itself, which I will briefly discuss in the time remaining. So a few implications that you can think of for the dark sector cosmology is, firstly, let's talk about the large energy release from the phase transition. This is about 0.9. Now, if your dark sector is completely decoupled from the standard model, this essentially redshifts radiation, and it is subject to strong constraints from Big Bang nucleosynthesis and CMB observables in the form of delta N effective. So what you need to do is you need to dump some of this energy. You release some of the energy from the dark sector that came from the phase transition into the standard model. So this really implies that, yes, there are portal interactions between the dark sector and the standard model. You can think that, okay, if it's redshifting as radiation, that's a problem. Why not have it as dark matter? Let's look at the mass spectrum with just the U1. So from the PTA fit, we learned that the dark Higgs mass is about a few MeV, say 3 MeV. The gauge boson mass is about of the order of 10 MeV, and your fermionic mass, if your Yukawa coupling is non-zero, is about say 5 to 10 MeV. So what happens for the best fit is that your dark Higgs always emerges as the lightest stable particle. It can be a dark matter candidate, but the problem is that you're hit with the overclosure constraint. The relative density is simply too large. So what you need to do is you need to, again, release some of the energy stored in the phi field into the standard model. So you need some portal interactions. So you can see both pictures. So you need a portal for consistency. And releasing energy is not so easy given the constraints. So for example, the easiest thing you can think of is that why not have phi mix with the standard model Higgs? Then you can, yeah, through mixing, you can have this thing decay, and then, yeah, this should work out fine. Unfortunately, this doesn't work at about a few MeV. The degree of mixing required ends up having this phi being too long-lived during BBN. So this is completely killed. A possible option we found could work through some back of the envelope calculations is that if you have kinetic mixing of the dark photon with the standard model photon, this can allow phi to release enough energy and acquire the relic density through the forbidden channel. Another possibility is through what's known as the elastically decoupled dark matter channel, but I do not have too much time to go into this. This is another possibility that may or may not work. Sorry, rather can work. But as we were really focused on the gravitational waves, we leave proper studies, dedicated studies for this dark sector cosmology to future work. And I've now come to the conclusion of my talk. So hopefully I've convinced you that dark sector phase transitions can indeed offer a very good explanation for the PTA signal. How we showed this is that we took an underlying particle physics model. We delineated the particle physics model at the Lagrangian level, so really honed in on the model parameters and studied the parameter space that can account for the PTA observations. What these data sets revealed is that the PTA signal really defines your underlying dark sector. And once this is defined, what we saw is that for the best fit points, you need a large amount of energy released from the dark sector during the phase transition. And this needs to be dumped into the standard model. So portals are necessitated. And this offers a complementary avenue with experimental searches, such as laboratory or astrophysical searches. And in certain scenarios, I briefly mentioned that you may be able to get the correct amount of dark matter, with the dark matter mass being a few MeV or so. And with that, I have come to the end of my talk. And thank you once again for the invite and the opportunity to present my work. And I'd be happy to take questions.
Great, thank you very much. Super nice talk. So are there questions? Joel, please.
Yes, thank you. I need to leave for a meeting in 5 minutes, so thank you very much for the very, very nice talk. I enjoyed it very much. So yeah, during the whole talk, I was wondering what would be the impact of the portal interactions on your results regarding the phase transition, right? Because right, you present very nicely the impact on these alpha, beta parameters, on the temperature, on mu and lambda, But if you add a portal with the Higgs or with a kinetic mixing with the B mu nu, I was wondering how would your results change?
So so the kinetic mixing is kind of straightforward. What you really need is, why is this not working? Okay. So what's really happening in the effective potential, if I can get the slide right. So what you need is the field dependent mass. So the epsilon B mu nu, sorry, or F prime mu nu, F mu nu, that is not a field dependent mass coupling to the complex scalar. So that does not affect the phase transition itself. In principle, so if you add something like a lambda prime phi squared h squared term, that in principle can impact it. But the difference is that yeah, the separation of scales is quite different. So this is at MeV scale, and the electroweak phase transition, so to speak, is at GeV scale. So because you have such a large separation of scales, this would have a minor impact.
I see.
Yep.
I see. Great. And the mixing with the mixing with the Higgs would be exactly the same, right? You could have some kinetic mixing, not with B mu nu, but with F mu nu. No, but then again, you say that it's not even with the photon.
Yeah, but this doesn't affect the phase transition. The
Yeah.
only one that could kind of affect the phase transition is that lambda prime 8 squared phi squared. But because the scales are so different, it
Yeah,
really.
then it's
And
okay.
anyway, that coupling needs to be very small to avoid the Higgs mixing constraints.
Super. Okay, thank you very much. And thanks again for the fantastic webinar.
Thank you. Thank you.
More questions? I have one for now. So you say that if you want to fit nanograph and PTA, uh, the temperature for the phase transition is like 2 point or around a couple of MeVs,
Around
right?
2. Yeah.
Yes, but then you have to be careful with the BBN, I imagine, because it's
Yes.
happening after. So I was wondering, so I think it's not a problem because the energy stored in the dark sector is always subdominant with respect to
Actually,
more.
there
So
is
it's
a
not
slight
really.
problem. So even if you have a portal releasing energy, you can still affect BBN because of this large alpha star. These guys
Mhm.
had shown this. The temperature that we're taking, this is just about safe. If you want it a little better, what you would have to do is kind of, so the easiest way out is compromise the fit by raising the mu a little bit. So you have to
Yeah.
compromise the fit, then you're definitely safe. But yeah, so at this point, it's relatively safe, but there is a danger actually. You can affect,
Mhm.
yeah, there is technically a danger. So this point is just about safe, these points.
Okay, and what about the duration? It has to be short or long? I don't remember.
So it has to be a very long phase transition. Here, there's yeah, for the duration, I don't think there is such constraint for BBN, I think.
No, because if it's very, very long, I know, but these scales, these are all relativistic. So, yeah, so I think it's fine.
Yeah, for
Yeah, no, then it's fine. I was thinking
B,
if it scales like matter, but no, this should be radiation. Okay, cool. Okay, that's fine from my side. Any other questions from the chat? I don't see anything. Um, okay, another technical question. In your plot, when you show no nucleation and no first order, so no nucleation is just that this gamma is never equal to h power 4, right? That's not
yes,
nucleation.
yeah, that equality is never met.
Right. And for no phase transition, is that there's no
No,
barrier at all?
uh, rather, okay, so when you do so rather the barrier is numerically small. So to really
Okay, but
understand
how do you compute that?
so you can actually compute the height of the barrier and just use it in terms of like normalized units. So what you can kind of do is you can just compute the height of the barrier. I put a
But
cutoff in
I
the
mean, it's not the high, is the high or this V over T?
it's delta V,
Mm-hmm.
the delta V divided by the lambda V 0 fourth. So that's how I normalize the barrier. So if the barrier height, I put a cutoff at say, let's say it's less than 10 to the power minus 6, if I recall in my numerics, 10 to the power minus 6, then I reject that point or classify it as not first order. So that's a
Okay,
really small barrier. Yeah.
but that's kind
Uh,
of arbitrary,
it's
right?
kind,
That
it's
number,
a little
that
arbitrary.
cutoff.
Yes, it's
see.
a little arbitrary. So if you actually relax it a bit more, take it to 10 to the power -7, what would happen is you would end up with a few more points here, and so on and so forth.
I see.
So for us, like really what was important was the so we were taking a bit more care for the no nucleation points, because that's particularly what we want.
Okay, excellent. Great. So if there's no further question, I just want to thank you again, Amitayus. Fantastic talk.
Thank you.
And yes, so I
again.
remind viewers that we have another webinar is next week, no, in 2 weeks' time. So it will be July the 2nd, so exactly in 2 weeks. Okay, thank you very much, guys.
Bye.
Hey.
Okay, we are off.